metathesis reactions.
Does it have to do with salts, or are salts just a mix-up?
You could have salts in different kinds of reactions. It doesn't have to be metathesis. But metathesis reactions require salt usually, or compounds. They're favorable ion combinations. That's what metathesis reactions are. And so we'll have an AB, which is some ionic compound or some compound, plus CD. And what forms when we have an AB plus CD combination? What we do is we just try a different pair of ions. Rather than A being paired with B, we'll pair A with D. And so we end up with A now with the D anion, and B is going to be paired with C. So C is the cation, B is the anion, so it's CB. What you're seeing is which side is more favorable. Is the product side, this is the product side, or the reactant side more favorable? Well, we need to know what are favorable ion combinations. So what are favorable ion combinations? Favorable ion combinations we're going to call a driving force, DF. Favorable ion combinations will form like a precipitate. Precipitate's PPT, precipitate. And precipitation is the formation of an insoluble solid. An insoluble solid has strong bonds holding the ions together. The bonds are these electrical forces we call electrostatic or coulombic forces. And if they're strong, then the solid won't dissolve. Or the reverse of that is if those ions encounter each other, they'll come together and bond with one another to form an insoluble solid. We can precipitate to form a solid. We can also precipitate to form a gas, but I'm not going to call a gas precipitation. We'll just call it gas formation. In terms of gas formation, some ion combinations will result in gas, like hydrogen ions and cyanide ions. Hydrogen ions and cyanide ions result in hydrogen cyanide gas. Excuse me. Hydrogen ions and sulfide ions will result in hydrogen sulfide gas, etc. So these are gases that form due to the combinations of those ions. Or B, we could have hydrogen ions and carbonate ions. When hydrogen ions and carbonate ions come together, it forms H2CO3, which we call carbonic acid. But the thing about carbonic acid is it decomposes. It's unstable. And so let's put a little asterisk there. It decomposes into H2O, liquid, plus CO2 gas. And so this would be carbonic acid, H2CO3 aqueous. And so we say it spontaneously decomposes. And so in this case, CO2 gas would form. So these are some gases here. C. Sulfurous acid is also unstable. And sulfurous acid decomposes into H2O, liquid, plus SO2 gas. So SO2, HCN, H2S, those are all toxic, poisonous. CO2 can be toxic, but you'd need much higher concentrations. Whereas you don't need much HCN or H2S or SO2. What's this called? NH4OH. Ammonium hydroxide. Ammonium hydroxide is unstable too. It decomposes into ammonia plus H2O liquid. Now ammonia is either aqueous and or gas. Depends on how warm the solution is, but ammonia is normally a gas and it can vaporize out of solution. So this is gas formation. However, CO2 is not very soluble, so all of the CO2 pretty much bubbles out. And the same thing with SO2, it's not very soluble. NH3, on the other hand, is quite soluble. It's a lot like water. So most of it will stay dissolved in water as aqueous ammonia. A little bit might come out as gas, and if you heat it, then you can drive out the ammonia as a gas. Excuse me. So those are some gases that could form. 3, if we go from a stronger acid on the reactant side to a weaker acid on the product side, so this is also a driving force as well. Stronger acids are more reactive, less stable. So stronger acids are more reactive, less stable. Whereas weaker acids are less reactive, more stable. So when we look at all these driving forces here, 1, precipitation, 2, gas formation, 3, stronger acid to weaker acid, all these we want to form more stable products. So driving force is going from less stable reactants. Now we can do this in terms of height here, because the higher we go, the more energy we have and the less stable it is, versus lower energy, more stable products. So this is a driving force, what we call. However, if we go in the uphill direction here, then we say that there's no driving force. So let's say if instead of going down, the products are actually less stable than the reactants, then this is no driving force. We want to go downhill here. And so this would be no driving force. Or if it's, close to the same. So what we want to do is we want to go downhill. We want to form these stable products is what we're after. So let's take a look at acids right now. In your supplement, you have this chart here of the acids. You have your 7 common strong acids here. And then there's going to be a border. The border is hydronium. Yeah. And then you have your weak acids. The way they rank the acids is, at least the acid strength is by how easily the acid loses its hydrogen. And so we know that strong acids are strong electrolytes. Let's do this.
Are we going to have to memorize this, or is this going to be given to us in the chart? Or
Okay, do you have to memorize this chart, or is this going to be given? That's going to be given. It's going to be given, but some of the footnotes and side notes on this won't be given.
Okay.
Just the chart itself.
no, that's what I was talking about, was just the chart itself. I was like,
Just the center part of the chart.
Okay.
The names aren't going to be given.
okay,
You'll have to figure out the names.
okay.
Strong acids are strong electrolytes. Strong electrolytes completely ionize or completely dissociate or completely hydrolyze in water. So let's take the strongest acid there. The strongest acid there is called perchloric acid. So if we look at perchloric acid, it's a strong acid, so in water it should completely ionize, making it an excellent conductor of electricity. And so this is about 100% or 100% ionization. We say strong electrolytes completely ionize, which would be 100%, but in reality, it's close to complete, but not 100% complete, 99.99 whatever percent. But I talked about H+. Do you remember last week? What did I say about H+? It's a proton. What did I say about the proton's reactivity? Is it stable or unstable? I said it was very unstable. Why is it so unstable? Yeah, it's, well, +1, is that really all that big of a charge? +1?
It's very small.
Yeah, exactly. It's not all that impressive of a charge, but when you compare its size, you know, how big is a single proton? A single proton is incredibly small. You know, it's a subatomic particle. And so it's incredibly small, making it highly reactive. So H+ aqueous is terribly unstable, and it doesn't exist as H+ aqueous. So even though I might write this, H+ will immediately attack water. And when H+ attacks water, it forms hydronium, H3O+. And so even though this is a strong acid here, this strong acid, the way you don't buy hydronium, you have hydronium. The hydronium is a result of H+ attacking water, that's all. How much hydronium you have is going to be dependent on how strong the acid is. Strong acids, you have lots of hydronium, because all these are strong electrolytes. Strong electrolytes break apart completely. Weak acids partially ionize. And the stronger the weak acid, the more hydronium. The weaker the weak acid, the less hydronium. And so you get less and less hydronium as you get weaker and weaker. We can easily measure this by a pH meter. A pH meter measures the hydronium content in a solution. And so, for example, if the hydronium, and I have square brackets here, the square brackets means concentration. As the hydronium ion concentration increases, the pH actually decreases. It's inversely proportional. And so the strong acids all have low pH. And then the pH starts to rise because you get less hydronium. And so something like trichloroacetic acid is going to have less hydronium. Therefore, it's going to have a higher pH. So if we're dealing, we're going to look at pH later on in the semester, but if we have 0.1 molar, that is 0.1 moles dissolved in a liter of solution, that's what we call 0.1 molar, then these have a pH of 1. But trichloroacetic acid would have like a pH of 2, and then pH just increases. Eventually we hit water, which is going to have a pH of 7. And so the pH increases because we're going to get less and less hydronium as we go. All right, but how should we write this then? What should we do about H+? So we have two options. One, we just leave this as is. We leave this as is, knowing that H+ is not so stable. So when I see H+, in reality, H+ is actually hydronium. But I don't want to hassle with this. Or two, we know automatically H+ is unstable. Or we could think of it this way. If we have water present, then the HClO4 will react with the water. So we'll call this the acid. Water will be the base. And what we're going to form is hydronium directly and perchlorate ion, like this. And so this is about 100%. These two equations are equivalent. The reason they're equivalent is because we know that free protons don't exist anyway, and that should be replaced with hydronium. But it's less writing, and so sometimes we'll write it like this on the top, sometimes we'll write it like this on the bottom. On the bottom, it's like this. This is just an acid-base reaction. Acids are proton donors, bases are proton acceptors. The base in this case accepted a proton to form hydronium, and the acid lost a proton. When it loses a proton, all we're left with is perchlorate ion. So that would be in terms of acid-base. And so the top one we call ionization or dissociation. The bottom one we call hydrolysis. Hydrolysis is just reacting with water. Hydro for water, lysis for reaction or breaking apart water. It doesn't really break it apart, it just adds a proton to it. So this is called hydrolysis or acid hydrolysis. To be more specific. So the strong acids ionize or hydrolyze completely. And the weak acids partially ionize or partially hydrolyze. And so to a lesser extent. So if we pick a weak acid, let's pick nitrous acid here. If we look at nitrous acid, HNO2, then there are two ways we can think of this. Actually, I forgot the aqueous. Here, this should be aqueous. Sometimes I'll leave off the aqueous. In fact, most of the time I leave off the aqueous because aqueous is by far the state that you're going to encounter the most. And so if we leave off aqueous and write liquid for liquids, G for gases, and S for solids, then we're okay if we leave off aqueous. And so for nitrous acid, HNO2, we can come up with two equations. The first equation is it partially hydrolyzes, and when we do partial, it's actually very little, H plus and NO2 minus. We can measure the pH. When we measure the pH, we can figure out how much. ionizes or how much hydrolyzes. Because the pH meter just measures this. It doesn't measure HNO2. It measures the H plus of the hydronium concentration in there. And so based on the pH meter, we can figure out, how much we start with here, how much we end up with here. And we can quantitate that. And so I showed two arrows there. And basically, the big arrow is pointed in the downhill direction. So this is more stable. So this is downhill. And the small arrow points in the uphill direction. This is uphill, so this is favored downhill. Whereas over here, this is the downhill direction. It's like this. And we can figure out what's uphill and what's downhill because the stronger acids are less stable or more stable. The stronger acids. Less stable. So this is uphill. And then the weaker acids are more stable. So this is going downhill this way. And so if we compare HClO4 with hydronium, HClO4 is up here and hydronium's down here. Do you see? So in terms of the acid, we're going from a stronger acid, HClO4, to a weaker acid, hydronium. It's downhill. Whereas in the second reaction, okay, this is the acid ionization reaction here. But it's the same thing as the acid hydrolysis reaction. Here, HNO2 plus water yields what? Excuse me. The acid is a proton donor. The base is the proton acceptor. So this is the acid, this is the base here. So we're going to form hydronium and NO2. What's the charge on NO2? Minus nitrite. So here we're going from nitrous acid to hydronium. Is that uphill or is that downhill? So if we look here, we're going from nitrous acid to hydronium. Is that uphill or downhill? That's uphill. So is that very favored? No. Therefore, we write the small arrow in the uphill direction, the big arrow in the downhill direction. Do you see this is more stable than that? And so what happens in this particular case is that we have a huge population of nitrous acid molecules and water molecules. And when I look at that huge population of nitrous acid, let's say I have 1 mole of this and a bunch of that. If I have a huge population, are all the nitrous acid molecules moving exactly the same? That is, they're in sync like robots? Or are they moving differently? In other words, let me ask you this. Do all the water molecules move exactly the same? Or are they going to have different rotations, vibrations, translations? Victoria, you say no. What do you guys, other guys think? Are they moving the exact same, in sync? Or is it random? It's kind of random. And so what happens is that, this is uphill, and a small population of these can make it uphill. Most of them will stay downhill. This is like if you have a big group, and you're all riding bicycles, and you see a hill coming up. Does everybody want to challenge themselves and ride up the hill? No. I mean, a lot of people will just stay down at the bottom of the hill. It's fine. But there's always going to be that few that will want to go up, and that will result in this. And so we'll have partial. And how much ionization just depends on how big that hill is. The bigger the hill, the less. Downhill's no problem. If we're going downhill, everybody can make it downhill. But uphill is more difficult. And so these ones, the hill's not so big, So to go from trichloroacetic acid, this is a typo, this H should be on the end here. To go from trichloroacetic acid to hydronium, is that a big hill to climb? No. But to go from, let's say, acetic acid to hydronium, that's a much bigger hill, do you see? And therefore, When I look at trichloroacetic, a bunch can make it up the hill, a bunch of the bicyclists. But when I look at acetic acid, it's going to just be a small fraction. And that small fraction turns out to be less than 1%. And so if I look at all the acetic acid molecules, only about less than 1% will be able to make it up this. And therefore, we're going to have less than 1% ionization. So let's take a look at the acids here. So, when you have tables like this, one of the things to do is just to read the table. This is another way you can learn things, just by repetition. We can name these acids. Can you name these acids without looking at the name here? So HClO4 is perchloric. What's HI? Hydro.
Acid.
Hydro what?
Hydroic acid.
Hydroic acid and ioic?
No.
Hydroiodic acid. Hydroiodic acid is correct. HBr? Hydrochloric. HCl? H2SO4? Yeah, sulfuric acid, chloric acid, nitric acid. Hydronium is a product of H plus and water, but that's where it would rank here. So you wouldn't go to the store to buy hydronium acid. It would be like hydrochloric or any of the other acids, which would be producing the hydronium. Now, the interesting thing here is that since this is downhill, 100% of the molecules can make it downhill, right? And so what this means is that these acids, another way of thinking about it is these acids are too strong to exist in water, because they're all going to go downhill to form hydronium. And so what we say is that hydronium ion is the strongest acid that can exist in water. So if we have nitric acid, the nitric acid will react with water completely to form hydronium and nitrate. The chloric acid, same thing, etc. All these are going to react with water completely and go downhill to form hydronium. And so when we look at the reaction, we don't have those acids anymore. So let's take a look here. So perchloric acid reacts with water about 100% to form hydronium and perchlorate. If we have 100% reaction, how many molecules are left over? None. They all went downhill. There's nobody left at the top of the hill. Everybody's at the base, at the bottom of the hill. And so what we say is that the major species, there's only one, and there's no minor species. And so the hydronium and perchlorate over here are the major species. And for strong acids, there are no minor species because there's nobody left at the top of the hill. Everybody could make it downhill. Does that make sense? And so we expect 0 molecules. And therefore, what we can say is that these acids are too strong. They're all going to go downhill. And there's going to be nobody left. Therefore, there's no minor species of molecules here. However, with weak acids, we don't say that. In weak acids, this is uphill here. And so weak acids will form a little bit of hydronium, but most of it stays downhill. So the major species here are just like nitrous acid molecules here. And the ions would be the minor species there. And so weak acids can exist in water. So this is the major. In fact, they're the major species. And the ions would be the minor species. So this wouldn't light up the light bulb as bright here, because the molecules don't conduct electricity. Why don't the molecules conduct electricity? Molecules of HNO2. What are they lacking?
They don't dissolve in water.
They dissolve in water.
But then they don't dissolve as much.
They don't. I mean, I'm just saying the molecule. The ions will conduct electricity, so it does dissolve. It does conduct electricity because of these, but it doesn't conduct electricity because of this. Why doesn't this conduct electricity? These will conduct electricity, this doesn't.
Because it's not an ion.
Hmm?
Because it's not an ion form, it's not charged.
Yeah, because there's no charge, right. And so the electrical, if the molecules of the major species is not conducting any current. Does water, pure water, conduct electricity? No. Just the minor species are conducting. So this is going to give us a dim light bulb. So trichloroacetic acid is the strongest of the weak acids on this chart. And then we have this one, H2C2O4. What's the name of that? This is
Oxalate.
oxalate, which is going to make oxalic acid. Maybe not quite ready for it yet. HCl2 is called chlorous acid. HSO4 minus is called hydrogen sulfate ion, or another name for it?
Sulfuric acid.
No. H2SO4 would be the sulfuric acid. We would call it something else. What would we call it? Hydrogen sulfate ion or sulfuric acid is H2SO4. This is HSO4 minus. No, I mean, if hydrogen sulfate's correct, what's another name for hydrogen sulfate ion? Bisulfate. I think it's a bisulfate. Bisulfate, oddly enough, is stronger acid than phosphoric acid.
But why is it called bisulfate?
Why is it called bisulfate? Somebody named it bisulfate. And most people call it, most people don't call it hydrogen sulfate. You know what most people call it? Bisulfate. Most people call it bisulfate, and therefore you should know bisulfate. What's this? Nitrous acid we talked about. HF? What is it?
Try out this is it.
Here you can see the pattern. If the anion ends in IDE, then the acid is hydrofluoric acid. Iodide ends in IDE. The acid is hydroiodic acid. Bromide ends in IDE. The acid is hydrobromic acid. Chloride ends in IDE. Hydrochloric acid. Sulfate doesn't end in IDE. What else ends in IDE? Let's take a look. Cyanide ends in IDE. Do you see? And therefore the acid is hydrocyanic acid. Any others? Amide ends in IDE, but it doesn't work here. These are rules, remember? And rules are There's exceptions to rules. So these ides don't work. But these ides are very unusual. I'll talk about these ides shortly.
So are we supposed to know all of these plus some extra cations?
Are you supposed to know all these?
Yeah.
Like memorize them?
Yeah. For the test.
No, you don't have to memorize them, but you have to know how to derive them. If you don't know how to derive them, then memorize them. If you know how to derive them, then you don't have to memorize them. It's up to you. Some people are good at memorizing and they don't mind memorizing, and they'd rather memorize it than derive it because they don't want to think about the rules for deriving it. And so if you don't want to memorize, if you don't want to know how to derive it, then I recommend memorizing it. So HClO4 is perchlorate, and what do we do with eights? Ic acid. So this would be perchloric acid. Sulfate, sulfuric. Chlorate, chloric. Nitrate, nitric. Trichloroacetate, yeah, trichloroacetic acid. Oxalate, oxalic acid. Sulfate, well, this sulfate forms sulfuric acid up here, but to form the acid anion, bisulfate. Phosphate, phosphoric. Nitrite, nitrous, yeah. Formate, formic acid, etc. So as we go farther down on the acids, these become more and more stable. Becoming more and more stable, it means it's less likely to lose the proton. And so it becomes more and more difficult to ionize and more difficult to hydrolyze the proton off of these acids. Then we come to water, which isn't a very good acid. It'd be considered quite a weak acid here. But these are even weaker than water. This one we don't normally consider acidic. This is ammonia. Hydrogen gas, we don't consider that acidic either. Bisulfide, hydroxide. Those really aren't.
Imagine what water is in terms of acidity and how it works here. So, is it trying to say that water is not very good at dissolving in water?
Water is excellent at dissolving in water.
Okay.
Yeah.
But is there still a chance that it might light up the light bulb? Even though there isn't, but it isn't all the way down.
There's a current. We need a certain amount of current to light up the light bulb. It turns out that there is a little bit of hydronium and a little bit of hydroxide in water, but it's so little it doesn't light up the light bulb. But it would carry a current. The current is extremely small. Not enough to electrocute you, and so that's good. So basically these really struggle to act as an acid. In fact, if you look at the climb here, like if we take a look at the worst acid here, hydroxide, and we look at the acid hydrolysis of hydroxide plus water. Now, we're going to treat hydroxide as the acid here, and water is the base. What forms here?
Could hydronium form?
I'm sorry?
Could hydronium form?
What?
Hydronium?
Hydronium? No. Oh yeah, hydronium forms, right. Hydronium and what else? And O2 minus, oxide. Now, how high of a climb is this? So if we start off with hydroxide at the bottom, and then we climb up to hydronium, how high of a climb is that? Actually, I should go on the full chart here. So if we start off with hydroxide here at the bottom, and we end up with hydronium at the top, how high of a climb was that? That was pretty high. What percentage of the population do you think can make it that high?
Close to zero.
Close to zero. In fact, zero. It's pretty much zero. It's so small. And so what we say here is this is too high of a hill to climb. Too high of a hill to climb. So hydroxide is way down here, hydronium is way up here. Too high. So we can put that in words over here. These are too weak to be. Now, Bronsted-Lowry is the type of acid we're looking at, Bronsted acid. Bronsted acid or Bronsted-Lowry acid is a proton donor. And so these are too weak to be Bronsted-Lowry acids in water. In other words, that hydroxide is not going to react with water. It would be too big of a hill to climb to form hydronium and oxide. And so these are so weak as acids we don't even really consider them acids because it's too big the hill. All right, we have the acids on the left side of this chart. What do we have on the right side of the chart? On the right side of the chart we have the bases. And there's a conjugate relationship. So if we look at the acid perchloric acid, perchloric acid is a strong acid, meaning it ionizes or hydrolyzes completely. That means the H plus is easy to break off. Whereas something like hydroxide is extremely weak acid, that means the H plus is very difficult to break off. If the H plus is easy to break off, then we lose that, and then we're left with perchlorate. Perchlorate, though, a base is a proton acceptor, so perchlorate doesn't have a strong attraction for H plus. If perchlorate had a strong attraction for H plus, then it wouldn't let it go. And so we see the link here, the bond between H plus and perchlorate is very weak, therefore allowing the H plus to leave. That means perchlorate isn't a very good base. And so if the acid is strong, what we call its conjugate base, that is this pair here, is weak. There's a seesaw relationship. So if one side's strong, the opposite side is weak. And so this is strong, meaning all these are extremely weak bases because they all lose their H plus easily, and they all don't have a strong desire to get another H plus. Let's see. So these are very weak bases, too weak to be Bronsted-Lowry bases in water. Now, bases do this. Bases can hydrolyze water. And so if we look at something like perchlorate, actually, let me go back. ClO4 minus. This is a base, in water, if we have water present, let's say we don't have any perchloric acid, we just have perchlorate and some other cation like sodium perchlorate or something like that. Perchlorate can take a proton from water to make perchloric acid and hydroxide. This is called base hydrolysis. This is terribly uphill, but it's an inverted hill here. So the bottom of the hill is here. The very weak bases, these will be at the bottom of the hill. On the acids, this is the top of the hill. And so these are all the top acids here. But where are the top bases? The top bases are on the opposite end of the chart. Here. I'll just look at it here. These would be the top bases here. And the top bases here are actually so strong that they don't exist in water. So let me get that. So if we take a look here, is that hydroxide ion is the strongest base that exists in water. So we can't have any base that's stronger than hydroxide that exists stably in water. Why is that? And so let's take a look at amide ion here. The reason why amide doesn't exist in water is because it reacts with water. And when it reacts with water, it takes a proton off water. So this is aqueous to form, okay, what forms here? So amide's going to take a proton off water and form what? Ammonia. And water is going to be converted to hydroxide. Okay. Yeah. So we're going from amide to hydroxide. Is that uphill or is that downhill? Okay, the funny thing is, on this chart, this is the downhill direction. But we have this inverted relationship, the seesaw relationship here. So on this chart, this is the downhill direction. The downhill is actually uphill, so maybe I should change the wording, but I changed it. And so we're actually going downhill. So if you're with a group of bicyclists, will everybody be able to make it down the hill? I think so, yeah. Everybody can make it downhill. And so what we say is that this, strong bases hydrolyze water completely. Strong bases hydrolyze about 100% here. And that's because it's downhill like this. Let's look at a weak base, like for example, cyanide. So this is downhill in the base universe. But if I'm at cyanide here, cyanide hydrolyzes water. What forms? So cyanide is the base, B. Water is the acid, A. What forms? This is aqueous.
Carbon dioxide?
Not carbon dioxide.
No monoxide.
No. Bases are proton acceptors. Acids are proton donors.
Was there a pair of car keys left in here? Did you
Did email? Did you see some car keys around there?
No.
Danny, can you check on the floor or the seat? How about under your backpack there? Yeah. Let me know, Nicole.
Is there a place I can go to look for lost?
Yeah, you could, the stockroom has lost and found, and the office over here, Natural Science Division office. If you walk through the corridor there out towards the corner of Manhattan Beach Boulevard and Crenshaw, there's an office on the left. The office, you can ask them and they found it. And also the police, call the police if it was dropped on the sidewalk or something. Somebody might give it to the police. So what are we going to form? Well, cyanide's the base. It's a proton acceptor. A proton is H+. So if we take an H+ and a Cn, what do we make? Hydrocyanic acid. And if water loses the H+, what are we left over with? Hydroxide. So we're going from cyanide to hydroxide. So cyanide to hydroxide is actually uphill because we're inverted now. On this side, downhill's down. On this side, we're inverted, so downhill's actually up. So we're going downhill here, but we're actually going uphill in terms of energy. These are high energy here, or less stable. These are low energy over here. When I say high energy, it's not kinetic energy I'm talking about. What kind of energy am I talking about? Hmm?
Something like electricity.
Electricity?
No, something related to electricity.
Related to electricity?
To electrons.
To electrons? I'm just talking about what are the two kinds of energy? Potential and kinetic. This is not high kinetic energy. This must mean it's high potential energy. High potential energy relative to what? Relative to the weak bases. These are the strong bases here. The weak bases are going to be low potential energy. And so as we go up here, it gets weaker and weaker. In fact, the weakest base on this chart is, do you know what the weakest base on this chart is? So as we go up, it gets weaker and weaker and weaker, and finally we hit the weakest base on the chart, and the weakest base is perchlorate ion. In fact, perchlorate ion is so weak that we say it's too weak to be a base, a Bronsted-Lowry base in water. What that means is that it's too far uphill. So if perchlorate were to try to act as a base, this is what would happen. For cyanide, it's a little bit uphill. So going back to cyanide just for a moment, if it's cyanide and you have a big population of bicyclists down here, then a number of them will be able to make it up here. Not all of them, but some of them. And so this is a weak base. Weak bases do what? They partially hydrolyze. Strong bases hydrolyze 100%. Weak bases partially hydrolyze. Partially hydrolyzed because not all the bicyclists are going to make it to the top of the hill. Just some fraction of the bicyclists will make it. But if you have something that's so weak, perchlorate, and we call it too weak to be a Bronsted-Lowry base in water, according to that. What that means is that if I take perchlorate in water, what would I form? I should form cyanide. This is the downhill direction. So the bigger arrow I'm going to make as the downhill direction. The smaller arrow here I'll make as the uphill direction. And so this will be uphill, this will be downhill. So it's going to make what? It's going to make perchloric acid and hydroxide. Now, how big of a hill is this to climb? And how big of a hill this is to climb is we look here. Where's perchlorate? Here. So we're going from perchlorate to hydroxide. And so perchlorate's at the very bottom of the hill. The very bottom of the hill is where it's most stable, the very weak base. And then we got to climb up, 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 up as we're going down the hill. I mean, not down the hill, but down the table until we hit hydroxide. Is that a big hill to climb? Yeah, that's a big hill to climb. In fact, it's so big that we say that nobody's going to make it up, unfortunately. Nobody makes it up because it's too big of a hill. And so it could try to make it up, but it'll fall back down. And so the population stays down here. So this is the conjugate relationship. There are different ways of thinking of the conjugate relationship. One way of thinking of it is weak acid means that it holds on to the H+. It doesn't let it go. If it holds on to the H+, that means oxide has a high affinity for H+. And therefore oxide is a powerful base because it wants to get an H+. And hydroxide is a very, very weak acid because it doesn't want to give up its H+. And so the seesaw relationship is this. Strong base means weak conjugate acid. So strong base means weak conjugate acid. The conjugate acid is here, hydroxide. And likewise, over here, if we have perchloric is a very strong acid. It gets rid of the H+ easily. That means perchlorate has very little affinity for the H+. So strong acid means very weak conjugate base. So this is the seesaw relationship. It looks like this. If one side's strong, the other side's weak, and vice versa. Now, there are some species that appear on both sides of the chart. For example, water. You know, water can either act as a base or it could act as an acid. It's weak on both ends. But there are other species that are like this that we call amphoteric, like hydroxide. Hydroxide can act as an acid, but it's too weak really to be considered an acid, or it can act as a base. Well, as a base, it's very strong. These are all the strong bases here. Hydroxide, in fact, turns out to be the strongest base in water because all these will go downhill. So hydride will go downhill to form hydroxide. Sulfide will form hydroxide. Oxide will form hydroxide. So hydroxides will be the strongest. These will completely hydrolyze water to form hydroxide, whereas these ones, the weak bases here, will partially hydrolyze water. So phosphate's the strongest of the weakest bases, of the weak bases, and therefore it's going to hydrolyze the most to produce the most hydroxide. And then as we go and get weaker and weaker, we form less and less hydroxide. Now, the bases are going to have the opposite effect as the acids, hydronium. There's going to be a seesaw relationship between hydroxide and hydronium. So the more hydroxide we have in solution, the less hydronium. And the more hydronium we have in solution, the less hydroxide. So we're going to have some kind of balance between hydroxide and hydronium. And so that's our acid-base type thinking. So if I have a base like, let me grab a base like ammonia here. Which of the three scenarios is it? Well, we know bases hydrolyze water. And so if ammonia hydrolyzes water, what do we form? We're going to call it a base. Ammonia could act as an acid too. Here's ammonia as an acid here, which is too weak really to be an acid. And here's ammonia as a base, which is a moderate base. Ammonia is a pretty decent base. And so we're going to say that ammonia is the base, water is the acid. What forms? Yeah, hydroxide and ammonium. That's correct. Hydroxide and ammonium. Which of these three scenarios is it? Is this going to be downhill, a little uphill, or a lot uphill? In other words, is this going to hydrolyze completely, partially hydrolyze, or not hydrolyze at all? It should partially hydrolyze. So it is uphill, but it's not so far uphill that nobody can make it. And so we get some partial hydrolysis here. Whereas, let's take another example here. Sulfide in water hydrolyzes water. Sulfide is the base, water is the acid. What forms? Okay, when we do this, we're just going to do one. And so we'll form bisulfide, just one H plus at a time. It would form hydrosulfuric acid eventually. But it's going to form bisulfide and hydroxide. So is this...
So the acid gives a proton to the base?
The acid gives the proton to the base, yeah. Is this sulfide, is it a strong base, a weak base, or too weak to be basic in water? In other words, is this downhill, or just slightly uphill, or uphill so much it's not going to happen? This is downhill. We're going from sulfide, which is stronger, and on the base chart it's inverted, remember? This is the top of the hill. The top of the hill is the strongest bases. The strongest bases are the most reactive bases and the least stable. So sulfide is near the top. It's second from the top. And so if we're at the top of the hill, the only way we can go is like down this way here. So if sulfide goes to hydroxide, that's downhill. Well, everybody can make it downhill. If everybody can make it downhill, then it's going to be complete or 100%. And we expect this to completely hydrolyze. And so this is why we say that sulfide is too strong to exist in water. It's too strong to exist in water because it's going to react with all the waters here, as many as it needs to form these. And this will be downhill. So all the sulfides can react, leaving none there. And so sulfide's too strong to resist in water. They're all going to react. And so this is 100% strong base. All right, so let's take a look. We're going to take a look at the supplement here for some practice. The supplement has a mix of reactions, and what we're going to do is we're going to look for double replacement reactions. Double replacement reactions are going to have a pattern to it. What was the pattern again? AB plus yeah, so we're going to look for this pattern, AB plus CD. So it turns out number 1 is not a double replacement, but number 2 is a double replacement. So let's take a look at number 2 here. And I'm just going to do it on the PowerPoint. I don't like number 2 for Chem 4 that much. Maybe for Chem 1B it's okay, but even for Chem 1A. But since we're stuck with it, I'm just going to go with this. Hydrogen chloride. What's the formula for hydrogen chloride? HCl. Solid, liquid, gas, or AQ? They say it's bubbled, so it must be, if you're going to bubble something, it must be a gas. It's bubbled through aqueous lead-2 acetate. What's the formula for lead-2 acetate? Lead-2 is Pb with what charge? And do you recall the formula for acetate? C2H3, O2, negative. And so what's the correct ratio to balance out the charges? 2 acetates. We need 2 acetates for every lead. And so we'll just put those in parentheses here. 2 acetates. And it's aqueous, so we use the AQ there. So as far as our AB plus CD pattern goes, hydrogen chloride, A is hydrogen, B is chloride, C is lead-2, D is acetate. So what we're going to do is we're going to take hydrogen chloride and we're going to take the hydrogen with acetate. And so rather than hydrogen with chloride, we're going to make hydrogen with acetate. And then the chloride is going to go over here and combine with lead. So what we're going to form is hydrogen acetate and lead-2 chloride. Do you see that? So over here we're going to take the H plus and the acetate. Well, H plus and acetate are going to combine in what ratio? how many acetates do I need for every H plus? 1. And so it'll form hydrogen acetate and lead 2 chloride. So how many chlorides do I need for every lead? 2. So we have hydrogen acetate and lead 2 chloride. Okay, this is not balanced. But before we balance, we're going to look for a driving force. There are 3 driving forces. 1, precipitation. 2, gas formation. 3, stronger acid to weaker acid. And so the first thing is, we'll look. What is hydrogen acetate? Its name. It depends. It's going to be aqueous. And we don't call it hydrogen acetate. Do you know what we call it? Acetic acid. So we're forming acetic acid. So over on the product side, we have acetic acid. Over on the reactant side, we have hydrogen chloride. Well, hydrogen chloride, if you bubble it through water, do you know what's going to happen? If we bubble hydrogen chloride through water, it dissolves in water, and we form HClAQ. HClAQ is called hydrochloric acid. So if I take my hydrogen chloride gas, bubble it through water, I'm going to form hydrochloric acid. Or leave it alone as hydrogen chloride gas. In quotation marks. Because what's going to happen is the HCl gas is going to react with water immediately. What's the strongest acid that can exist stable in water? Is hydronium or H+. We use H+ and hydronium interchangeably, although we know hydronium is much more stable than H+. And so the strongest acid that can exist, we can't have HCl molecules in water. It's too strong. We can have HCl molecules in air, but not in water. So that's why I'm going to write quotation marks around here. Okay, so what we're doing is we're going from hydrochloric acid on the reactant side to acetic acid on the product side. Are we going uphill or downhill? We're going downhill because we're going from what we call an SA. SA stands for stronger acid. It doesn't have to be strong, it just has to be stronger. And HCl happens to also be strong. To WA. WA means weaker acid. So we're going from the stronger acid to weaker acid. And we call that a driving force because this should be downhill. Stronger acids are higher energy, less stable. Weaker acids are lower energy, more stable. And so we have a driving force here. Stronger acid to weaker acid. All we need is one driving force. And we're okay. This reaction should proceed, but this reaction has 2 driving forces. What's the other driving force? Can you see it? Precipitate. Is chlorides, bromides, and iodides are all soluble except for lead, lead 3, lead, mercury, and silver. And so this is not one of the exceptions. Therefore, this is this is one of this. Excuse me. This is one of the exceptions. So this is insoluble, and so it's going to form an insoluble solid, which we call precipitate. And so the other driving force that's present is this precipitation, or precipitate. And so 2 driving forces: 1, stronger acid to weaker acid, and 2, precipitation of lead 2 chloride. Okay, let's balance this, and then we'll take a break here. How many hydrogens do I have? 1 here, I have 1 here, so those are balanced. How many chlorines?
2.
1 here, but 2 over here. So this is not balanced, so I'm going to have to double this. That gives me 2 chlorides and 2 chlorides. How many leads? 1, 1. How many acetates? I have 2 acetates here, I only have 1 acetate here. I'm going to have to double that. If I double the acetates, that's going to double the H pluses, which I need to happen over here. And so this would be balanced. All right, let's take a break now for 15 or so, and then come back. Resume this. Okay, what do we call HCl gas? Hydrogen chloride. And HCl aqueous we call hydrochloric acid. And they're saying we are adding hydrogen chloride as the gas here. And so if we were to try to visualize this, what we have here is a solution of lead-2 acetate. And in this solution, we're going to bubble the gas. The gas is just going to be pure hydrogen chloride gas. And what should form here? Yeah, a precipitate of. So the precipitate I'll just hash out. It's going to be a solid precipitate of lead-2 chloride, PbCl2. And in solution, we're going to have what? Acetic acid. Now what we're going to do is, this is what we call the CE. What we're going to do is something called the IE, or the ionic equation. In the ionic equation, we ionize the strong electrolytes. Weak and non-electrolytes we leave alone. And so we're going to ionize just only the strong electrolytes. The strong electrolytes are what? Strong electrolytes are strong acids, strong bases, and soluble salts. Now that this particular problem is kind of a challenge problem, because what do we do with HCl? You know, the strong acid would be hydrochloric acid, HCl aqueous, but they gave us HCl gas. In reality, if I have HCl gas is soluble in water, and it's going to ionize because it's a strong acid. But since they're giving us HCl gas, we'll just leave it as HCl gas. So it's a little bit ambiguous what we should do with HCl gas. And so I'm just going to leave it as HCl gas here. That's what we're using to bubble in here. And so the way I think about this is, in this particular case, I have a choice. I can get a tank of HCl gas, or I can grab a bottle of HCl aqueous. In this particular reaction, am I grabbing the bottle of HCl aqueous, or am I grabbing the tank of HCl gas? I'm grabbing the tank of HCl gas. And so I'm just going to leave it as HCl gas here. Some people might differ.
So the ionic equation is
So I'm going to leave HCl as HCl because the acid should be a strong acid. All right, the next reactant here is lead-2 acetate. In the ionic equation, do I ionize lead-2 acetate? So I'd ask, is lead-2 acetate a strong acid? No. Is lead-2 acetate a strong base? No. Is lead-2 acetate a soluble salt? Acetates are all soluble, and so yes, it's a soluble salt. So I'm going to ionize it. What does it ionize into? So it's going to break up into ions. What ions would I form? Pb2 plus acetate. How many acetates? 2. And so it's going to break up into 1 lead ion and 2 acetates. And then let's look over at the product. PbCl2. Is that a strong acid? No. Is that a strong base? No. Is it a soluble salt? PbCl2. It's not a soluble salt. It's an insoluble salt. So if it's not one of those 3, just leave as is. And so we're going to leave that as is. Plus 2 acetic acids. Acetic acid, is that a strong acid? No, it's a weak acid. If it's a weak acid, just leave it as is. So what the ionic equation shows us is it shows us the major species. In this case, the major species here for the lead acetate solution is going to be Pb2 plus and acetates, C2H3O2 minus in here, C2H3O2 minus. So even though the beaker is labeled lead-2 acetate, AQ, what's contained inside that beaker are lead ions and acetate ions in this ratio. It's a 1-to-2 ratio.
what happened to the hydrogen?
What happened to HCl?
I see what happened to the chloride. Like I don't know what happened to the hydrogen.
The hydrogen went to acetate. The chloride went to lead. And so the H plus went to acetate to form acetic acid, and the chloride went to lead to form lead-2 chloride. Do you see?
Oh, I didn't see
So
that.
it gets split apart.
Okay.
in this case. But we left the HCl as a gas here. If this were HCl aqueous, then I would have broken it apart into H plus and Cl minus. Okay, now the net ionic equation, the NIE, is eliminating anything that doesn't react. That is, anything that's the same on the left and right sides of the reaction. So HCl gas changed. Pb2 plus changed. Acetate changed. And so there are no spectators. And so the NIE is the same. No spectators. A spectator would not change. So, for example, Pb2 plus on the left and a Pb2 plus on the right. That would be considered a spectator. But here we have Pb2 plus on the left, but we have PbCl2 on the right. And so it's not the same.
How would you know when they're going to be spectators?
You'll see that they're the same on both sides. For example, if I have acetate here, acetate and acetic acid are different. But if I have acetate here on the left and acetate on the right, then those are spectators. We can cancel those out. Okay, let's take a look at the next reaction. Number 3. This is from the supplement. And what they want you to do in the supplement is to do the full formula equation, which I call the complete equation, complete formula. The total ionic equation, which I call the ionic equation, and the net ionic equation, which I call the net ionic equation. So let's do that for this next reaction here. Aqueous solutions of iron 3 sulfate and ammonia are mixed. And so the first thing we need to do is get the correct formula for iron 3 sulfate. And so what's the formula for the iron 3 cation? Iron 3 cation. Is it IR3? Fe3 plus. Sulfate? SO4 2 minus. And so we could do this trick with the charges, that is, we'll just use the charges for the subscripts here. And so the correct formula will be Fe2 SO4 3. And then ammonia, what's the formula for ammonia? NH3. And so this is going to be Fe2SO4 3 aqueous plus NH3 aqueous. Now, when we look at this, does this have the AB? Yes. This is our AB. A is iron. B is sulfate. But what's our CD? Do we have a CD here? And when I look at this, this is not a CD. What's the cation? What's the anion? And so this is not going to be a CD. You might say the cation's N3 plus and the anion's H minus, but this is molecular. So for molecular compounds, we don't always think, unless it's an acid, we don't really think in terms of cation and anion here. And so this does not look like a double replacement reaction. So it appears it doesn't fit. Metathesis are ion combinations. Ammonia is not an ion. But there's something you should know about ammonia. And what is ammonia? Can you name a chemical property of ammonia? Have you seen ammonia before? Did I forget? Oh, I did. Have we seen ammonia before? Yeah, we did. Ammonia is an acid, right? Ammonia is an acid, but what do you know about ammonia as an acid? It's too weak. You don't really consider it much of an acid, unless you have an extremely powerful base. We don't. But we've seen ammonia not on the left side here, but we've also seen it on the right side here. And as a base, these are the strongest bases here, so it's a moderately strong base.
Why is ammonia a weak acid?
It doesn't want to lose the hydrogen. And it doesn't want to, so this comes from observation. And so you might say, well, why doesn't it want to lose the hydrogen? Well, that's just what's observed. And so you're going to have this chart. You don't have to analyze it structurally. There are structural arguments why it's weak, but we aren't getting into those yet. And, so if you were to try to figure out, it'd be kind of difficult to figure out. It's easier just to look it up on the chart. This chart is going to be given. In fact, this chart is right there. So it's available. You don't have to memorize this chart. On tests, I'll give you the chart. But when I give you the chart, it's only going to contain these middle columns here. It's not going to have the names. So one of the chemical properties of ammonia is it's a strong base, weak base, or too weak to be even considered a base.
So that was base?
It's a weak base. Yeah. And what do weak bases do in water?
Partially.
Yeah, they partially hydrolyze water. Well, that's going to be important here. Does not look like a metathesis. Ammonia is not an ion. However, ammonia is a weak base. Ammonia is a weak base, which means partial hydrolysis. So ammonia will partially hydrolyze water in what forms? I'm sorry?
NH4.
NH4 charge? Plus one. And hydroxide. All right, so we looked at this chart before, and it's not terribly uphill. So we're going from ammonia on the reactant side to hydroxide on the product side. So yes, it is uphill. You know, the top of the hill is oxide here. It is uphill, but not terrible. So that we are going to get some hydrolysis to occur. Well, you might look at the percentages and you might go, that is terrible. Let's take a look. How many? Well, about 99% of the bike riders are going to stay at the bottom. Maybe only 1% or less will make it up to the top of that hill. That's how many. So it's very little. You know, it's not an impossible hill to climb, but most of the population stays down below. So if you had 100 bike riders, only one would make it to the top. The other 99 would be at the bottom. Okay. But, you know, it turns out that even though that's very little, that's enough to react. We don't need that much to react. And so what we're going to do is we're going to treat this. We're going to form a little bit of ions. We're going to treat this as my CD. And so that's my AB over here. This is going to be my C. This is going to be my D. And my CD is going to be, I'm going to call it ammonium hydroxide. That's my CD. And so over here, I'm going to rewrite this. I'm going to say that I have iron 3 sulfate plus ammonia plus water. Now, aqueous, as I said before, aqueous is so common. It's the most common state that we're going to be encountering. So I don't want to write it. I mean, that's 3 more characters here. I mean, 4, you know, parentheses, AQ, parentheses. There's 4 more characters here to type or write. 4 more characters here. So what I'm going to do from now on is I'm going to leave off aqueous. If I leave off aqueous, then I have to make sure I write liquid L, gas G, and solid S. And so I'll put in the other states. Just leave that. So what we're going to do is we're going to treat this as if it's just ammonium hydroxide. In reality, it's ammonia and water. I mean, it's 99%. And so it's just a little population of ammonium hydroxide. But that little population of ammonium hydroxide is enough to react in this case. And so what we're going to do is we're going to go AB plus CD. So we're going to have A, the iron 3, with D, hydroxide. And so if I take iron 3 and hydroxide, what's the correct formula? So if I take iron 3 and hydroxide, what's the charge on hydroxide? Negative. How many hydroxides will I need to balance out the positive charge? I'll need 3 hydroxides. And so I should form iron 3 hydroxide, which will be FeOH3. And I'm going to take ammonium with sulfate. Ammonium is a plus what? 1. And sulfate is a negative 2 or 2 minus. And so how many ammoniums will I need to balance out the charge? 2. And so that's going to form NH4, 2, SO4. And so even though this does not look like a double replacement or metathesis, it turns out it is. And so this is, in fact, a metathesis reaction. However, I'm not going to write ammonium hydroxide. I'm going to leave it as ammonia and water. Why am I going to leave it as ammonia and water? Because it's mostly ammonia and water. I want to leave it just as a major run it. All right, before I balance this, I want to determine if there's a driving force. And so the first thing you look at is precipitation. Did we form any precipitates? Did we form any precipitate?
Does the iron hydroxide inside?
Yeah, hydroxides are all insoluble except for
Group 1?
group 1, ammonium, and
No, group 2.
not all of group 2.
Some.
Which of group 2?
Calcium, strontium, and barium.
It's calcium, strontium, and barium. It's not one of the exceptions, so this is insoluble. So we say solid precipitate. All we need is one driving force, and we have it here. And therefore we expect reaction to occur. This is a downhill reaction. And so we can tell by the formation of the precipitate here. It's going to be downhill. Is ammonium sulfate, does that also precipitate? No, all ammonium salts are soluble. Does ammonium sulfate decompose into a gas? No, it doesn't decompose into a gas. Just the ones I listed. Are we going from a stronger acid to weaker acid? This is more complicated, so we're not going to look at that. And so all we need is one driving force. We have that one driving force. This is it. So let's go ahead and balance this. Now balancing it, the easiest thing to do is not leave it as ammonia and water, but balance it according to ammonium hydroxide. And so the way we balance this would be, I have 2 irons here, I have 1 iron here. So I'm going to have to multiply this by 2. And so that gives me 2 irons, 2 irons. The irons are balanced. Then I balance the sulfates. I have 3 sulfates here. How many sulfates do I have here? 1. And therefore, multiply by 3. So that gives me 3 sulfates. And then how many hydroxides do I have here? 6 hydroxides. And then how many hydroxide? I have no hydroxides here until I look down here. When I look down here, how many hydroxides do I have? 1. So I'm going to multiply this by 6. Well, if I want 6 ammonium hydroxides, then in order to get that, I'm going to need 6 ammonias and 6 waters. And that will give me 6 ammonium hydroxides. So that gives me my 6 hydroxides. And then how many ammoniums do I have? 6. And that balances out. And so this would be balanced here. And so the CE is going to look like this. We're going to have our Fe2SO4 3, iron 3 sulfate. I'm going to leave off AQ because it takes 4 characters like that, plus 6 ammonias, plus 6 waters. If I leave off AQ, then I have to put in the state for everything else. This is going to make 2 iron 3 hydroxides, solid, plus 6 ammonium sulfates. This is the full formula or the complete equation here. Note that ammonium hydroxide doesn't really belong there because if you go to buy the chemical, you're going to buy ammonia, aqueous ammonia, which is going to contain some ammonium and hydroxide. All right, next we go to the ionic equation. The ionic equation, we ionize the strong acids, we hydrolyze the strong bases, and we ionize the soluble salts. So iron 3 sulfate, strong acid? No, it's not one of the 7 common strong acids. Strong base? No. Soluble salt? Yes, sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So this is soluble. And so we ionize it. What does it ionize into?
Iron.
Iron?
Iron 2 plus.
Iron 2 plus? Or iron 3 plus?
Oh, it's iron 3 plus.
Iron 3 plus. How many do we need?
2.
2 of these. So we get 2 iron 3 plus, plus
So,
sulfate. How many sulfates?
3.
Okay, then we go to ammonia. Is ammonia strong acid? No. Strong base?
Is it not? Wait. Oh, it's at the bottom of this. Sorry.
Yeah.
Temperature.
It's a weak base, actually. Soluble salt? It's not a salt. It's a molecular compound. And so if it's not one of those 3, we just leave it alone. Water, is it a strong acid? Strong base? Soluble salt? No, just leave it alone then. Don't do anything. Iron 3 hydroxide, strong acid? No. Strong base? No. Soluble salt?
What's some salt? I don't know.
A salt is an ionic compound that's not an acid. So any ionic compound is a salt, basically. Unless it's an acid. If it's an acid, we name it differently.
There's like
So is it a soluble ionic compound or an insoluble ionic compound? That's a salt, but it's easier just to say salt. Is it a soluble salt or an insoluble salt? It's an insoluble salt, and therefore leave it alone. Ammonium sulfate, is that a strong acid? Strong acid? No. Strong base? No. Soluble salt? All ammonium salts are soluble. No exceptions. And so this is soluble. And so let's go ahead and balance it. What are we going to get? Did I get it right? Or did I screw it up? I guess I did. I screwed it up, sorry. I didn't quite balance it correctly. This shouldn't be 6, this should be 3. So we're going to dissociate this into ions. How many ammonium ions total? And how many sulfate ions? 3 sulfate ions. All right, so this would be the ionic equation. And then we're going to have the net ionic equation. Net ionic equation, we look for spectators. Did the iron 3 react or spectate? It reacted. Did the sulfate react or just spectate? In other words, did it change or did it stay the same? It stayed the same. So sulfate, let's get rid of that. Ammonia. Ammonia and ammonium are 2 different things, so this changed. Water, yeah, there's no water on the right, and so those change. And so the only spectator will be sulfate. So let's eliminate the sulfate, and so we're going to get 2 iron 3 plus 6 ammonia plus 6 waters. This is going to yield 2 FeOH 3 solid plus 6 ammonium. So we're visualizing this on 3 different levels, this reaction. On the CE level, it's just the chemicals you go buy at the chemical store. So at the chemical store, I'm going to go buy some Fe2SO43, aqueous. That's what we buy at the chemical store. But when we look at it, Fe2SO43 aqueous actually consists of iron 3 pluses and sulfates. And so these are the major species in solution. In another beaker, I'm going to have my ammonia and water. Ammonia and water is going to consist mainly of ammonia or ammonium. Aqueous ammonia consists mainly of ammonia. And we'll have water in here. We have lots of ammonia in there. All we need for this particular one is, like, for every iron we need 6, or for every 2 irons we need 6 of these. So yeah, but we have lots of them in there, in the water. If I have a bunch of these, I just need a little bit of them to react. You know, ammonia and water will partially hydrolyze to form ammonium and hydroxide. A little bit. And so there's a little bit of reaction in there. Not much. So for every, let's say, for every about 100 ammonias, we have 1. But I have much more than 100. I have much more than a trillion, usually. I have like a trillion, more than a trillion ammonias. And so for every 100 of those, if one of them reacts, I'm going to generate enough ammonium hydroxide to get this reaction to go. But I'm going to leave it as ammonia and water. You see? Ammonia and water. Why? Because that's what you're going to go buy. You're going to buy that, and then a little bit of that will react. If you try to buy ammonium hydroxide, it's not stable. It decomposes into ammonia and water. So. Then this is going to form iron 3 hydroxide precipitate, which is eventually going to sink to the bottom. And ammonium sulfate. No, I didn't draw all of them in here. Then if we look at the spectators, what are the spectators here? Spectator turned out to be sulfate. You know, we had 3 sulfates here as product, we have 3 sulfates here as reactant. So the sulfate is the spectator here. So the sulfate didn't change. We have 3 sulfates here, we end up with 3 sulfates here, and those cancel out. The others did change, like ammonia got converted to ammonium, which is different. And so the net ionic reaction is going to be the reaction between the iron 3s and the ammonium waters to form the precipitate and ammonium. That would be the net ionic equation.
Do we have to know like the ionic and ionic equations for the test? Like, are we gonna have a problem in which we're gonna have to know like the ions and which ones are getting dissolved in the water?
Yeah. The question is, do you have to know this for the test? And the answer is yes. You're going to have a question kind of like that on the test. So why don't you want to practice one? Let's do a practice one. Why don't you try manganese 2 acetate plus aqueous ammonia? Why don't you tell me the CE, the IE, the NIE, and the DF? DF stands for driving force, yeah. So tell me the complete equation, ionic equation, net ionic equation, and driving force. I would do the driving force with the complete equation. That way, if there's no driving force, then there's no reason to go on to the ionic equation and net ionic equation. So give this one a try here. Manganese 2 acetate and aqueous ammonia. Somebody tell me the formula for manganese 2 ion. Acetate? C2H3O2. Charge?
Minus
And therefore the correct formula for manganese 2 acetate would be?
Mn parentheses.
And then that's plus 2. We're going to need 2 acetates. That should give us minus 2. So Mn parentheses.
acetate. Two. Plus
We're-
NH3.
All right, so it's important to get the correct formulas there. And you have to figure out what to do next. Although it doesn't look like a AB plus CD double replacement reaction, it is, right? And so figure out how, based on the last problem we did. Some progress updates here. What did you do next?
I think, is it acetic acid?
Oh, little finishing the equation here. It's plus NH3 plus H2O liquid. This is going to produce what? Well, that's how we treat, what do we treat NH3 in water as? NH3 is a weak base, and weak bases partially hydrolyze water to form what? Ammonium and hydroxide. So this is my A, this is my B, this is my C, this is my D. So I'm going to have manganese 2 with what anion? With hydroxide. So what is manganese 2 hydroxide? The formula, did somebody get that? MnOH2. And we're going to have ammonium C with acetate. And so that's going to form ammonium acetate, which has the formula NH4 C2H3O2. And that's because manganese is 2 plus, and that would require 2 hydroxides. And acetate is a 1 minus, that just requires 1 ammonium. Balance that out. Is that what you guys got? Or we're working on?
I forgot the water.
Yeah, the water is kind of critical there. Why don't you balance it? Did somebody balance it already? Uh-huh, what did you get?
I got manganese, acetate, and a 2 ammonia, and H2O.
Okay.
And I get 2 ammonium acetate.
Yeah, that would be it. Like I said, the easiest is to balance it down here. So here we have 1 manganese, 1 manganese. 2 acetates, we only have 1 acetate over here, so the 2 needs to go in front there. That's going to give me 2 ammoniums. And so that means I need 2 ammoniums here and 2 hydroxides here. In order to get 2 and 2, I need 2 and 2 up here. And that gives me my 2 hydroxides for here, so that's balanced. Did anybody figure out the driving force? Precipitate. Which one is precipitate? Yeah. That would be it. And then we call this the CE. So that's it for the CE. And then somebody come up with the IE for me. Yes.
And then 2 plus.
I'm sorry?
And then 2 plus.
Mn2 plus, good.
Plus 2 C2H3O2
Plus 2 C2H3O2
minus
charge
minus.
minus. All right, that's because all acetates are soluble. Acetates, nitrates, and chlorates are all soluble. So it's a soluble salt. What do we do with ammonia?
So NH2.
Yeah, we leave it alone. What do we do with water? We also leave that alone. What do we do with manganese 2 hydroxide?
And then to the what?
Mn2 plus and 2 hydroxides? Is it a soluble salt or insoluble salt? Insoluble salts we leave alone. Only soluble salts. Strong acids, strong bases, and soluble salts are broken apart. Everything else is, it's an insoluble salt, so just don't do anything. Ammonium acetate,
That's soluble.
it's soluble. All ammonium salts are soluble, all acetates are soluble. So it's a strong electrolyte. What do we do?
2NH4
2NH4
plus
plus
2 acetate.
2 acetates. Negative. All right. Then we go to our NIE. So these are all the major species here. When we go to the NIE, what spectators do we have? Acetate. Anything else? No, actually that's it. So we get rid of that. Mn2 plus 2 ammonias plus 2 waters yields MnOH2 solid plus 2 ammoniums. The ammoniums are not spectators because ammonia and ammonium are 2 different things. This is balanced. Even though what happened to the acetates are still there, so that's going to charge balance positive. But what we have is net 2 plus on the right and net 2 plus on the left, or right and left, whatever, on both sides. And so it's balanced here. So that's another example of that. Now, let's try these next. Oh, that's wrong. All right, we'll do one more example of the aqueous ammonia. And then why don't you work on these ones? These are from the supplement. These are all double replacement reactions. There's more, but we'll just go with these for right now.
So
These are all double replacement. What's that?
do we do the aluminum?
Yeah, do aluminum. Did I do? We just did acetate. So let's change. Let me change this. I'm going to make this aluminum nitrate. and aqueous ammonia. So do aluminum nitrate and aqueous ammonia solutions are mixed. And then sodium fluoride, nitric acid, etc. So try these out here. You could work with other people. These are just practice. These aren't going to be a quiz. It's practice problems. Let me know if you have any questions. Try to help you.
Could this one work? Okay, yeah, so then it's probably this one. It might be that one. I'm like, cause mine has like this weird, like.
You like vomit later? It was still worth it.
January 6th, I was hanging out with my friends. What friends?
What friends? Where are your friends?
These people. Yeah, I was hanging out with my friend, her boyfriend.
Why'd you have to mention that? I know, it's such a strange thing to mention.
Well, you guys didn't even let me finish. Like, I hang out with my other friend who was like really crawling to a dress. And I hang out with my friend that's like this. Yeah, I was hanging out. I also hung out with this guy. But this guy was singing this.
Oh, that's crazy. It was a good set for the joke. Why are you so shocked that I would say that?
What'd you say?
Why are you thinking about that?
Imagine a short.
Ew! Bro, leave her alone. Leave her out of this, bro. Why is everyone obeying him? What the hell? Give me that shit.
He's not the same. No, no, no. Where were you then, Lisa?
Where were you? It was at the castle.
Where was I? My mom was my first that day. I was looking at that's why you're answering me?
Wait,
Where were you September 8th, 2022? Where were you September 8th, 2022?
2022 September 8th. Oh,
Where were you?
What are you talking about?
Grace, I want you to say it. September 8th, 2022.
some guy had like a 40 feet.
was this like a shooting?
No, better.
I accidentally missed it. I didn't see it.
September 8th, 2022. Kaz, where were you? September 8th, 2022. Yeah.
I could be.
Just like so fucking few battles.
Columbus here? What happened in Columbus? Here, type. My little brother always does that. I mean, oh, I was at oh. That's how I love running
Alright, I don't know.
No, you're a liar.
I got this part.
We gotta listen to the time.
I remember people have been making jokes back then.
Oh my god, Twitter was like a field day. I was laughing my ass off.
I was in physics when I told you. Like when they remember this, it always makes
Me
sense.
too. I forgot King, the King guy too. The mom King.
I told my teacher.
No, but yeah.
Everyone got white.
Did you get my King?
So like these two always.
There's no one here is British.
You could say that half of the leaders in
Fuck, bro, that dude was so bad.
Well, like,
I don't know what the balance situation is.
He was like, he's like,
I get it when you got your time.
guys, I want to apologize. Relax.
How was it say?
No, because he like predicted both. Because he was like something cool.
Why is this?
He was like something interesting.
Oh my god.
Yeah. Oh, it's really good. It was so hard.
No, if you're in physics. How much hours is that? How much hours is that? Wow. Oh, that's 3 days?
I go to a restaurant. I'm a company.
Wait, where?
What's happening?
Because I got A's.
You work Thursday? My friends are going to go.
Now I know where it's open.
I'm not walking back here and I'm
Start charging. A letter is crazy.
Where does it say that?
Anyways, I think let's do that. I disagree with your equation.
Okay, give it to me.
No, but that's fine though.
I guess. You're stupid.
Oh, wait.
Yeah, sorry about that.
Aluminum conductors are good at the charge more or less, and this is a charge of -1 plus 1. It's not balanced. It's 4. I kept out of that shit. There's too many things happening. Wait, I'm sure you put it like
'cause
Okay, you know the
Name a
C,
day when
I,
we did
and all that shit? Like the way he does like three different, he writes it 3 times for a specific.
Oh, no, that's not happening. That's the same.
You know what? You talk shit about her yourself.
Just like ionic.
I assume it's the C, because it's like the one that you know.
I was talking about her. You said I talked about her.
Guys, I'm doing it for you guys.
You see?
What do you want from me?
This lamp is like, it depends. And
I'm sure how Ashley had it.
See,
I use the one that charges usually.
yeah, these.
No, this is. I was just
Just like 1, 2, 3, negative 3, 2.
But what is this? No. I like it. I like it.
Yeah, that's what I was noticing. I did forget to shoot it, but I have it right
okay.
here.
I am going to say this stays like this because I think this is like this.
How is the
I think that's a good choice.
How is the
Wait, no,
This
I'm sorry. I mean, I'm rewriting, so I should like pull it down.
there's 3 finally.
But, I mean,
We don't even.
but I have,
So, the way you did like
yeah, I
the
have,
here,
that's
so
the.
when you add
Because hydroxide
A, it's so you make them already add the 3.
one.
And
Right,
already have.
I forgot.
It would have to be 4.
Yeah, put that in there. Because that's where that's like I. So, yeah.
I like that.
So usually when you write, you don't usually put it here, you put it down here.
So fix the formulas here.
So this guy has to
Nitrate equals 1.
instead of putting it like here, put it over
It should be 1 to 1, not 1 to 1.
Right, and I have it right here.
Yeah, that would be the IE.
This 3 should be down here, subscript.
I know you're right.
Here.
The charge, whenever you write the charge, it always goes outside. It doesn't really go here.
Kind of like
For
that.
any sort of the IE. But for the C, when you're balancing the
Then,
equation itself,
then this
you
should be
can put the
balanced.
3 over here.
See, except there you have 3 waters.
No, they're
You
wondering why we
have 3 waters.
Give us, yeah, why we don't put it here.
Oh, because it's all by the
So rewrite the formula.
Right.
And then this is
because I mean it says it's 33, and then if you have 3 nitrates, then it's just
They're balancing, to take each ammonia and each water is 1 ammonia.
I don't know, the way I remember it
And then
is
balance
this
it by
is
ammonium hydroxide.
Oh, that's
Otherwise
well,
it's confusing.
yeah, that makes sense. Like the
Yeah.
cross thing,
Okay, so
you
you're
can
gonna-
establish here,
You
and then
treat it, yeah, treat it as ammonium hydroxide. So you get 3 ammonium and 3
instead of like
waters.
saying that like, oh, they cancel out. I know it's like really
it's for the logic of it.
It's like plugging it in.
This is just what happens when you react.
So you have 1
Yeah.
aluminum, 1
To
aluminum,
get
then you
aqueous
have 3
ammonia,
nitrates,
you need to
and
have
then you
water.
put 3. The ammonium has to be written first. Caveats always first, 39 seconds.
So, ammonia doesn't like giving away station, like making it the current. Well, yeah, it likes taking it.
It's a weak acid. Or like
It's a weak acid.
It's a
It
weak
likes
acid, so
stealing
it
from the
wants
core.
Yeah.
it's a weak acid, so it doesn't want to
So you
It
have
won't
give
give
away
away.
their hydrogen.
It'll never give away nitrogen. It will steal it
That
from
could
other
be
things
3
like water
ammonia.
in order to make
And
itself
so
better.
you need
Or
3
anything.
ammonium hydroxides here. So there are 3
Yeah, so
down
then the
below.
water rewrites itself to the A.
No, you treat this
It
as
applies.
the weak acid.
but to get 3 NE4 OHs, you need 3 ammonium and 1 water hydroxide.
There is,
That's the top one
I
by
think
3.
a couple that don't do that.
And the water 3.
There's 3.
No, it's hydrogen.
It does have a nitrogen, so you don't need that for this one, you need the ionic.
Yeah.
So that's where you write it in down.
And then that's gonna give you,
So,
3 hydroxide.
Yeah, they don't balance
So
it.
you have 3 hydroxides here.
okay, so when you balance these ones, they have to do it on the same side, so like,
The reaction.
We didn't balance it, right?
I wanna check that.
Are you guys getting it there? Or?
I'm lying, I thought it was right behind me.
The thing was 9 of them. Then it's 9 of them.
Okay, so this is.
Did you say derivatives?
Bro!
It's so much easier than this. Derivatives are fun.
Derivatives are fun.
Because
The
there's
C
I
is
heard it
not
was
really-
fun, and I was
three
like,
on this side, or else it's not gonna be balanced. So you have to.
I haven't taken that. This is fun.
So then
Yeah, so like if there's two on this side.
This is literally 2014.
Let's go.
And the mark is not the reactive.
That's completely different. What does it mean? Because like, that one you're plugging in codes. And the other one you're.
I need to get a green cup in high school.
I hope I'm right. I'm very, very scared. I'm not.
Is that your turn?
I was losing fun.
Oh, yeah, this is the CE, this is the, I.
The C is gonna be,
You thought algebra?
in the equation, we just use ammonium hydroxide to help us predict what the product is gonna be, but we have to leave it as ammonium and water.
Oh, so we actually don't.
Don't change it to ammonium. You need to go back, to get 3 ammonium hydroxide, you need to go back to 3 ammonium and water. And so erase the ammonium and hydroxide, I don't have to charge it. Oh, damn.
That's AC test.
No,
Oh, wait, that one.
LAUSD under LAUSD for last year.
Yeah.
Games for all.
right, it would be 3
Me and my friends took like 15.
Dude, I had to pay for all
Nah.
So I'm going to
AP per.
then to balance it, you're 3.
This is like my.
Balance it, you use ammonium hydroxide. So for each ammonium hydroxide, you need 1
I mean,
ammonium
you're
and
not
water.
here.
You need 3 ammonium hydroxide, and you need 3 ammonium hydroxide.
No, I mean like it's part of LUSD.
I mean, I do.
It's part of LUSD. My soul.
Rancho Palo Verde.
But in the equation, you don't leave it ammonium hydroxide. You just use ammonium hydroxide temporarily to figure out the product and the balance. And so the C would be ammonium, so P2 plus.
Yeah, there's a lot of down here. There's not much to do like down the Lakewood. There's not much to do about that. You gotta come over here.
Yeah, C would be ammonium.
Why
and
do you
would
have
be
C?
hydroxide.
Yeah, there's a lot to do about USC. Because it's science
But Santa Monica still
Yeah.
have
no hope. Santa Monica Middle, but not that far.
How many columns are there?
Traffic.
Especially if you don't know.
Yeah, what, 13 miles?
I know this.
Truck, yeah.
So you forget the car.
It'll be instant.
What happened to the expectators of the other ones? Where's the flag?
It took me 30, it took me literally half, like an
All right, the
hour.
IE is incorrect though too. IE should translate, you still have to
I
balance
was just
it.
took the train that just
It's balancing it. And then ammonium nitrate is not written like that.
Oh, that's good.
Okay, what's that last thing?
What's your score?
What's your score?
No, down. Yeah, that one, down,
Perfect.
up, and all those. What do you name
I didn't
that?
get a perfect score, but
We don't talk about mine was crazy.
I passed it first time, they're gonna take my grade.
Sometimes are written
We're gonna work on
but it's
this.
not three.
Huh? No.
If you have 2 waters, would you write it?
I'm working on shit to
H4O
look on this.
Choose?
It's
No, you write it 2 H2O. If you have
This is so bad. Because I didn't know that my perfect picture was gonna go on my license.
that's a good point.
The driving test is.
You don't.
I had 15.
That's the subscript.
I had 15, so I was mistaken about that shit.
That was just me.
Forever. No.
I did check my Wikipedia. I was like,
I was thinking about going
I
to
drove so long
because it's so
I'm
bad.
like,
I did not.
I'm just crazy. I was thinking it's forever.
Ammonium's a cation, nitrates are in second.
I didn't want
So that should be like,
See my IG pictures.
Like his military one is better than like.
first thing I told you was.
In school, I did this.
Almost made him.
yeah, I took No, it's because the first time I didn't, the second time I didn't look at the book, third time I was like, no, third time I was like, I was just I never did this.
I had a bunch of weird questions.
Oh, what about from our
I think we should just make it.
No questions.
Okay.
I'm so mad. I
Grace, we just said like
I got a question that's already right.
yeah, but at least that's right. Our Chem version.
got all of your time. No,
The other option.
And you say you're not me.
Actually, I know we're going to tomorrow.
All right, we'll just continue tomorrow.
That's
Mr. Chabal, this is scary. That's scary. That's like everything that we've learned combined for this event. I don't know how to feel. It's not
Yeah, it's gonna be a lot of stuff.